Hello everyone, welcome to my channel. The first topic that we are going to start with is medium access methods in the Wi-Fi world. Now in the WLAN world, the MAC layer is responsible for a number of important functions. The function specific to our discussion here today that the MAC layer again performs is something that we call frame transmission. Now, what does this mean? So frame transmission essentially handles when should a frame be transmitted, who should transmit a frame, or how should a frame be transmitted. Why is this so important? It is because typically if you look at a BSS, it will be something like this. You have an AP, you have station A here, you have station B here. Station A can talk to station B or vice versa, or station can talk to the AP or the APs can talk to the station. Now all of these communications is happening on the same channel, or it is happening in the shared medium, which inevitably leads to the possibility of collisions. Now these collisions are often succeeded by something that we call as a retransmission or a retry. So naturally the more number of collisions, the more the retries. The more the retries, the lesser is the performance of the BSS, right? So uh, a large number of retries can potentially bring the BSS to a grinding halt. So how do we avoid this collisions, right? So the entire process behind uh, medium access methods here is to try and avoid as much collisions as possible in a shared medium. In order to do this, the standard has a couple of provisions in place. One is called DCF or distributed coordination function. The other one is called EDCA or enhanced distributed coordinated access. Now we will not be talking about this for long. This particular video and the upcoming series of videos will focus mainly on DCF and the subcomponents of DCF. DCF is essentially a set of methods which work together to reduce the possibility of a collision or to govern access to the medium. In other words, it is an implementation of CSMACA in the WLAN world. Now there are different components of DCF we will talk about as we progress towards the end of this topic. But to start with, one of the most important aspects of DCF or the beginning of how things start off in the WLAN world is by doing something that we call as a clear channel assessment. Now, as you might have guessed, the name means that the station or the AP is probing to check whether the medium is busy or idle. Now, CCA happens at two layers. It happens at the PHY layer and it can also happen at the MAC layer. CCA happening at the PHY layer is called as the physical CS or physical carrier sense. CCA happening at the MAC layer is called as a virtual carrier sense. Physical carrier sense can be of two forms. One is something that we call signal detect, the other is energy detect. Signal detect is essentially the ability of a station to detect the preamble of another transmission which is going on in the air. Energy detect is the ability of the station to detect raw energy above, let's say, a certain threshold. It's because the unlicensed bands that we use in Wi-Fi can be used or can be overlap with non-Wi-Fi sources of energy as well. So it's important to check for energy detect before deciding whether a frame can be transmitted or not. This usually also means that if the station has a 4 dB SNR, it can potentially hear a preamble of another station in the same PHY or the same channel. Whereas for energy detect, the generally the threshold is somewhere around 20 dB above the noise floor. Once the physical carrier sense is carried out, then the MAC or the virtual carrier sense comes into picture. Virtual carrier sense works on a principle of network allocation vector, which is a, a back off strategy which forces the channel to kind of wait before transmitting the frame, and this wait period is determined by the duration ID field in the ongoing frame which is being transmitted. Now, the duration ID is used to derive the NAV. The station waits for the NAV period to get over. If at all it hears a new frame in the meantime, the duration ID of the new frame is copied and then again the NAV is updated. Now let us assume that the station has indeed completed its CCA, right? So in a way, the MAC layer or the PHY layer reports to the MAC layer, right? So the MAC layer wants to transmit a frame. It waited for the NAV value, and then it checks with the PHY layer that, hey, can I still go and transmit a frame? And okay, it's clear to transmit. So what happens after that? If CCA is cleared, let's say this is the duration that the station has to wait for the CCA uh, to differ or to clear, it can't just go on and transmit over here. After the CCA period is done, the station has to wait for another period of time which is called as the interframe space. Now, as you might have guessed, this literally means the frame between or the space or the time between two frames. This is an additional differing period or an additional time that the station has to wait after the CCA is done. Now, we will talk about IFS in more detail in an upcoming short video, uh, along with a few other topics, but just to summarize, the IFS is a time which is a variable. It depends on the PHY which is being used, and it also depends on the type of the frame which is being used. What happens after the IFS? I have waited for a X amount of time for the CCA to finish, then I have waited for the IFS to finish. Now, even after the IFS finish, I have to wait again for a period which is generally called as the contention window. So contention window essentially means that it is an integer value starting from 0 to a certain value, CW min or let's say max, and the station has to select a number between this range, and the station then does a countdown timer or a back off from this number to 0, post which it can transmit. Now, what is this number? This number is essentially something that we call as a slot time. Again, a slot time is something which is dependent on the PHY which is being used. So every PHY will have a different slot time. So a contention window is nothing but a series of slot times that a station has to wait before it is ready to transmit. We'll talk about slot time as well in the next video when we cover IFS and what are the different slot times for different PHY, what are the different IFS waiting periods for different PHY. So if you think of it this way, the purpose of DCF is to randomize medium access so that the chances that two stations will start talking at the same time greatly reduces. And it uses all of the different parameters that we just said. It uses the CCA to check whether the station is busy or there is a preamble detect which is happening and the station can wait till the station becomes or the medium becomes idle. Post CCA, it also uses the interframe spacing to further randomize or further distribute the chances that two stations might start talking at the same time, and also to some ways prioritize certain frames. Now, this is not the same as the COS prioritization, but it is giving different interframe spaces for different types of frames. And it also uses the network allocation vector or the contention window to further do a back-off algorithm or conduct a back-off algorithm and wait for a certain amount of time before finally the station can choose to transmit on the medium. In the next video, we'll talk about interframe spaces and see that how every PHY or every type of frame is given a different kind of IFS. and we'll look at the different IFS values for all of these PHYs.